In this video, we're going to try to summarize the various Fourier related things we've talked about. So if you have hopefully you've watched the series up to this point. So in the last handful of videos, we've talked about Fourier series and we've talked about Fourier transforms. And because they both are Fourier, sometimes we get confused in this one. And you can think about the Fourier transform as being a general purpose of the Fourier series. Another way to think about it, Fourier series is always periodic in time domain. So the signal has to be periodic in time domain to have a series, have a Fourier series. Fourier transform, on the other hand, is more general. It can be either periodic or this could be, your signal could be periodic or not periodic or aperiodic and in time domain, and that's fine. Both of those would work. So the best way to think about this is that the Fourier transform is a more general form. And then in time domain, we had two kinds of signals. We had x of t for the time domain stuff, and we had for the continuous time, and then we had x of n for discrete time. And then the whole job of these Fourier series and Fourier transform, all of them, the goal was the ability to be able to take the same signal into frequency domain and back in time domain. And this is a table which attempts to put them all in perspective. For example, if you look on the horizontal line, the first row is talking about Fourier series. So you're able to take x of t, which is periodic in time, and you can take it to frequency domain. So you will be knowing k is telling, the k will tell you which harmonic this magnitude belongs to. So if a of 1 says the magnitude in the first harmonic, a of 2 says magnitude in the second harmonic. That would be for the continuous time, and again, it's periodic in time, aperiodic or not periodic in frequency domain. Now, if you go to the discrete time, x of n, what you're going to get is that x of n is of course periodic, because in order to have a Fourier series, the signal in time domain has to be periodic. And this one happens to have a periodic a of k as well, and the a of k is going to have the same period as you have in the time domain, which is very nice for that. So, and as we discussed in the Fourier series side, you have to worry about convergence and all those issues. In the discrete time, you don't really have to worry about it, because your a of k is periodic, so it always converges. Periodic means it has a defined period, and you don't go from minus infinity to infinity, so you don't have to worry about things blowing up and not converging. Fourier transform, the second row, is the more general form, where it allows you that your x of t or x of n, your discrete or continuous, both can be aperiodic in time or periodic in time. It really doesn't matter. And then what happens is that, of course, your frequency domain, which we represent with x of j omega, is aperiodic in frequency domain. While when you go to the discrete side, x of e to the j omega is periodic in frequency. So that's another difference in that, okay? And as a matter of fact, we even know what the period in here is, which is going to be a 2 pi. Okay, so that's a summary of everything to do with Fourier series, Fourier transform that has been discussed so far.